In this lecture, we will explicitly show how a buffer resists changes in pH upon addition of a strong acid or a strong base. So in the previous lecture, we talked about how to prepare a buffer and how to determine its pH. Besides just measuring the pH, of course, you can calculate what the pH would be using the Henderson-Hasselbalch equation. So in this lecture, we will prepare buffers, at least on paper, and then we will show that when you add a strong acid or a strong base to the buffer, that buffer will resist changing the pH that would normally occur when you added a strong acid or a strong base to an aqueous solution. Recall the 0.1 molar acetic acid, 0.12 molar sodium acetate buffer in lecture 1, where we said the pH of that buffer was calculated to be 4.82. We set up this equilibrium to show our buffer equilibrium in solution, acetic acid on the left, acetate ion on the right. We said that there was 10th molar acetic acid in this buffer, 0.12 molar acetate from the sodium acetate. Remember, sodium ion is a spectator. And we can calculate the pH of this buffer by taking the pKa minus the log of the Ka value of the acid form and add that to the log of the ratio of the base form, which is acetate here, 0.12 over 0.1, and we get a pH of 4.82. Let's suppose you went into the lab and you prepared half a liter of this buffer, 500 milliliters. This would mean that the number of moles of acetic acid in this buffer would be the volume of the buffer times the concentration of the acetic acid, or 0.0500 moles of acetic acid. The number of moles of acetate would be 0.5 liters times 0.12 moles per liter, or 0.06 moles of the base form or the acetate. Now recall, we said because of the common ion effect, we can assume that when this buffer system reaches equilibrium, that the concentrations of the acid form and base form are very close to what they were initially. And so the number of moles of acid form and base form are very close to what they would be initially. So we can start with those. Well, we can say the pH of this buffer is equal to the pKa plus the log of the ratio of the number of moles of base form to number of moles of acid form. Remember, we said we could do that and use moles in the Henderson-Hasselbalch equation instead of molarities, and you get the same answer, pH of 4.82. Well, upon outside addition of a strong acid, and we're just going to signify strong acid by hydronium ion, to this buffer, the following reaction, which is actually turn out to be a manifestation of Le Chatelier's principle, occurs in the buffer. The acetate in this buffer is going to be attacked by the added hydronium ion. So this H3O plus in this equation is not what was here originally. It's the added H3O plus from outside. That added H3O plus is going to go after the base form and reform some acetic acid and water. We could also write this reaction more simply as the base form being attacked by a hydrogen ion going to the acid form. What I want to point out here is what's happening is in the buffer, and this is central to thinking about this, is that because we're adding an outside strong acid, we're changing the ratio of base form to acid form in this buffer because we're actually reducing the amount of base form and increasing the amount of acid form as the outside acid goes after the acetate in the buffer and turns it into acetic acid. So as I just said, the result here is that some of the base form is converted to acid form. Now, this is the central idea here. This is how the buffer resists the potential lowering of the pH by the added acid solution. In other words, when you add the H3O plus from the outside, it's not wandering around wild in the solution determining the pH. No, it gets captured by the acetate, and the acetate gets turned into acetic acid. So you're capturing the added hydronium ion. Well, what's going on here is that you're slowly turning the base form into the acid form in the buffer. So that will affect the pH, because if you look back up here at the Henderson-Hasselbalch equation, or at this form here, either one, you are reducing the amount of base form and increasing the amount of acid form. So this ratio is going to drop, but it's not going to drop very much. I should say the pH won't drop very much because you're taking the log of this changing ratio. So the pH does drop, just doesn't drop as much as it would if there was nothing standing in the way of that added H3O plus added to the solution. Well, what happens if you added strong base, a source of hydroxide from the outside? What would occur in the buffer? Well, kind of exactly the opposite. The base form that you add, this hydroxide, is going to go after, I should say, the strong base that you're adding is going to go after the acid form of the buffer, and it's going to turn it into the base form of the buffer. And the result is that some acid form is converted into base form, and that's how the buffer is resisting the pH going up drastically, because it's basically eating up the hydroxide that you're adding from the outside by converting some acid form to base form. Now the pH will go up some because, again, if you look at the Henderson-Hasselbalch equation, if you're converting acid form to base form, the amount of base form on the top is going to go up, the amount of acid form is going to go down. This ratio will get larger, and the log of that ratio will get larger, but not by as much as you might expect. So the pH will go up, but not as much as if you just put hydroxide into water and let it totally determine the pH by itself without any interference from the buffer. Now there is an alternate way to view the addition of strong base with the same result. And I think we've talked about something like this in the past in a previous lecture. If you refer to the equilibrium at the top of the slide here that we wrote for the acetic acid acetate buffer, if you add hydroxide from the outside, you could view this as an attack on the hydronium ion in the buffer. So suppose the outside hydroxide attacks this hydronium ion and turns it into water. Well, what's going to happen then is, by Le Chatelier's principle, this equilibrium will shift to the right, and resulting in a decreased amount of acid form and an increased amount of base form, which is exactly what we predicted when we looked at the reaction of hydroxide directly with the acid form, acetic acid. Let's do an actual calculation. Suppose you prepare this 500 milliliters of buffer that's 0.1 molar in acetic acid and 0.12 molar sodium acetate. As you saw in previous slides, this buffer is a pH of 4.82. So what we want to do here is calculate the expected pH after addition of 20 milliliters of 1.2 molar hydrochloric acid. Now here, of course, hydrochloric acid is a strong acid. The chloride that results from this will be a spectator. We're only interested in the hydrogen ions being added. We can actually recall from the previous slide that 500 milliliters of this buffer contains 0.05 moles of the acid form and 0.06 moles of the base form, and so we're asking how will this change after addition of the 20 milliliters of 1.2 molar hydrochloric acid? Well, before addition of any hydrogen, what's going on? We'll write our equilibrium here. There's 0.05 moles of acetic acid, 0.06 moles of acetate. How many moles of hydrogen ion are we adding? Now this is critical. If you look in our equilibrium here, we have numbers of moles under the acid form and the base form. So we're counting how many are there before we add the H plus from the outside. Now we're going to add H plus, but we want to count how many we're adding. The number of moles of H plus added is the volume times the concentration, or we're adding 0.0240 moles of H plus ion. Now this H plus ion, of course, goes after the base form of the buffer, which would decrease the number of moles of the base form and increase the number of moles of acetic acid. So the secret here to calculating what we think the pH will be after addition of the HCl is that we want to figure out how many moles of acetate we've lost and how many moles of acetic acid we've gained, and then subtract or add it to the number of moles already there. So here's my equation for the hydrogen ion going after the acetate ion. We assume, and we know, that since this is a strong acid reacting with a weak base, this reaction goes to completion. So after reaction with the hydrogen ion that we've added, what do we have? Here's our original equilibrium. We have the number of moles of acetic acid before H plus addition, number of moles of acetate before. Now since the H plus is going after the acetate, the number of moles of acetate is going to drop by the number of moles of H plus we've added. And on the other side, the number of moles of acetic acid, the acid form that we have, is going to go up by the number of moles of H plus that we've added. So after reaction with H plus, we have 0.0360 moles of the base form, acetate, remaining. We have 0.0740 moles of the acid form, acetic acid now, because we've gained 0.0240 moles from the reaction of the acetate with the hydrogen ion. So now we can calculate the new pH of the buffer using these new number of moles of acetate and acetic acid after reaction with H plus. So we have pH equals pKa, which is still 4.74, plus the log of the number of moles of acetate over the number of moles of acetic acid, which is now 0.0360 divided by 0.0740. So we get, and you take the log of that, and you get 4.74 minus 0.313, or a pH of 4.43. So remember, our original pH was 4.82, and adding 20 milliliters of 1.2 molar hydrochloric acid dropped the pH to 4.43. So notice the buffer did change pH slightly, but the pH did not drop off a cliff because the buffer is resisting the change in pH that would occur when you add this strong acid to the solution. So we have here the pH dropped by less than half a unit. One question you might ask is, do we need to be concerned about the dilution caused by adding 20 milliliters of the strong acid to 500 milliliters of buffer? The simple answer there is no, because we're counting things in numbers of moles, and we're going to see that again soon. So suppose you now prepared another fresh batch of 500 milliliters of buffer, that is 0.1 molar acetic acid and 0.120 molar sodium acetate. You just make a whole new batch. We want to now calculate the expected pH after addition of 20 milliliters of 1.2 molar sodium hydroxide, the strong base sodium hydroxide. Again, we're not interested here in the sodium ion, just the added hydroxides. So you can see we're adding just as much strong base this time as acid we added the other time. So the pH is going to go up. We're going to see how much it's going to go up and how well the buffer resists that pH going up. Recall from the previous slide that the initial state of this buffer can be written this way. And now this would be before addition of any hydroxide. Let's calculate the number of moles of hydroxide added. Well, not surprisingly, it looks like the same number of moles as we added of hydrogen ion because we had the same volume and concentration of a strong base this time. So we're adding 0.0240 moles of hydroxide. Well, what is the hydroxide going to go after? Well, on a previous slide, we decided we'd look at this as the hydroxide going after the acid form, acetic acid, and turning it into base form. So what we're going to have happen is number of moles of acid form is going to drop. The number of moles of base form is going to increase. And we wrote the reaction that we say goes to completion like this. So acid form being converted into base form from the addition of outside hydroxide. So after reaction with the hydroxide, what do we have left? Well, we wrote before hydroxide addition here. This is what we started with. Remember, the hydroxide's going after the acetic acid and decreasing this acid form by the number of moles of hydroxide that's added, 0.0240. And that means on the other side, the number of moles of base form is going to increase by that same number. So what we have here is after reaction with hydroxide, we have fewer moles of acid form. We have more moles of base form. Now we can take these two numbers here and put them in the Henderson-Hasselbalch equation. So now the number of moles of base form is larger than before. The number of moles of acid form is smaller. We get 4.74 plus 0.509 from this log term, or 5.25. So remember, the original pH of the buffer was 4.82, and adding the 20 milliliters of 1.2 molar sodium hydroxide, that strong base, raised the pH to 5.25, which is less than half a unit. Again, since we're dealing here in units of moles in the Henderson-Hasselbalch equation, there is no need to be concerned about the volume increase from 500 to 520 caused by the addition of 20 milliliters of 1.2 molar sodium hydroxide. So up to this point, our original buffer had a pH of 4.82. If we took 500 milliliters of that buffer and added 20 milliliters of 1.2 molar strong acid, HCl, the pH drops to 4.43, but it doesn't drop precipitously, so the buffer's resisting. If we made fresh buffer and added the equivalent amount of strong base, the pH would go up by about less than half a unit. So the buffer's resisting, but the pH does go up a little bit. So you might ask, well, I'm not really impressed by this resistance to pH change. I mean, after all, the pH did change. Well, what we can do, just for effect, is compare our results here to an unbuffered solution, such as water. So what we'd like to do is add this much acid or this much base to 500 milliliters of water that is not a buffer and see how the pH changes. If we assume the pH of pure water is 7, if we had 500 milliliters of it, we'd have a pH of 7. So let's just add 20 milliliters of 1.2 molar HCl to that. What would the pH be? Well, remember the number of moles of H plus added is 0.0240 moles. So we're going to simply take 0.0240 moles of H plus that we've added, divide now by the total volume, and we get an H plus concentration of 0.0462, and we'll calculate a pH, and it's 1.34. So if we add this 20 milliliters of 1.2 molar strong acid to 500 milliliters of just unbuffered pure water, the pH drops from 7 to 1.34. So in an unbuffered environment, the added HCl drops the pH by over 5.5 units. So up here, you said, well, the pH dropped, so maybe I'm not impressed. Well, now you can be impressed because this buffer was certainly resisting the lowering of the pH by the added strong acid, because if you add that much acid to water and let the hydrogen ions you're adding just run wild and run the show, the pH drops to 1.34. We can do an equivalent calculation for the addition of 20 milliliters of 1.2 molar sodium hydroxide. The number of moles of hydroxide added is, of course, 0.0240. We can calculate the hydroxide ion concentration in the water, and it's this, not surprisingly, the same number as you get up here. But you have to remember, if you take minus the log of the hydroxide ion concentration, that's POH, which is 1.34, but the pH is 14 minus the POH. So the pH is 12.66. So again, in an unbuffered environment, added hydroxide runs the show, runs wild, runs the show. The pH goes from 7 to 12.66, which is ridiculous. In the buffered solution, however, the pH only jumped from 4.82 to 5.25. So this buffer is resisting that added strong base. Let's try to summarize up to this point. We had 500 milliliters of 0.1 molar acetic acid, 0.1 molar sodium acetate buffer. The original pH of that buffer was 4.82. The pH after addition of 20 milliliters of 1.2 molar strong acid, HCl, was 4.43. It dropped some. After addition of the strong base, it went up some. We compared this to an equivalent volume of pure water, where the original pH would at least theoretically be at 7. It drops like a rock in the unbuffered solution, and it goes up like a rocket in an unbuffered solution upon addition of strong base. So the buffer is certainly more resistant to pH change than the unbuffered solution. One thing you might ask here is, can we make the acetic acid sodium acetate buffer even more resistant to pH change while maintaining the same original pH of 4.82? Well, we're going to leave that question and some other issues and maybe another example to part 2 of this lecture.